All right. Okay, cool. I think we're going to go ahead and get started. Everyone on Zoom, you guys can hear me okay, right? All right, perfect. I will take that as a yes. And I think we are good to go on recording. So yeah, thank you guys for coming out. I know it's Friday, so I appreciate you guys being here at lecture, especially 4:30. I don't know how it is wherever everybody outside of Boston is, but it is unseasonably warm today. So thank you for making it out, despite it being a Friday afternoon that is warm in January. Today, I think we're gonna have a lot of fun. So today's lecture is going to be the first in a series of 3 where we really focus on just puzzles or phenomena in nature, and we work on visualizing that. So it's really going to be the meat of the course. And we get started with one of my favorite topics, which is fractals and chaos. So if you're familiar with fractals, if you've heard of fractals before, and then you probably know how cool they look, and it's exciting that we're going to be able to generate fractals today using just a couple of lines of code. If you're not familiar with fractals, we'll get into exactly what they are in just a second. Administratively, if anybody is following along with the assignments, assignment 2 was posted yesterday on the GitHub. It was just a little bit late, but remember there is no official deadline on any of these. So feel free to take a look if you were interested in the content of the last lecture, and feel free to share that work if you guys are finished with any of it. Okay, so that being said, today's format for the day, we're going to run through like 4 or 5 quick slides. It's going to be super short and simple, and then we're going to head over to the Blackboard and processing to do a little bit of visualization. I know last lecture, we took the full hour and a half. I cut out some of the content on strange attractors today, and maybe I'll do like an addendum video if you're interested in any of that. But today we're just going to focus on fractals, and so my hope is we can go a little bit more in depth with that stuff, and we can slow things down just a little bit if anybody has any questions. Okay, so let me go ahead and share my screen, and we can get started. Can everybody see that okay?
Looks good.
Awesome. Okay, cool. So, if you guys will recall, we ended last lecture by creating this coffee cup visualization. And this was a really cool visualization because not only did it help us visualize our first pattern in nature, but it also helped us ask a lot of these what-if questions that are really important and interesting to us when we get into generative art. Today, I want to start just by extending that idea. So if you remember the original coffee cup visualization that we created, that was with the multiplication value of 2, that has this sort of like kidney bean-like shape inside of it. And it turns out this shape mimics the Mandelbrot set. And we'll talk about what the Mandelbrot set is in just a second. You can see it on the right here. It's a fractal. And so it's really cool how a lot of stuff in nature is a fractal, including something that we've already visualized. We'll give a couple more examples of what they look like in just a second. But this is one that we've already explored, and so that's nice and fun. Okay, so let's get into the meat of things. What is a fractal? Again, a lot of you have probably heard of fractals. You might have engaged with them in some of your like classes in math, anywhere otherwise, but we'll cover them very briefly. So fractals at their core are just structures with infinite self-similarity. And this is going to be really interesting to us because they, like I said, pop up lots and lots of different places. Now, one important thing to note is that depending on the definition that you're using, this might be infinite self-similarity. If we're talking about fractals purely mathematically, we are talking about like infinite self-similarity. But oftentimes, especially if we're talking about fractals in nature, they're not going to be patterns that are perfectly self-similar or infinitely self-similar. They're going to have qualities that are self-similar. And so you can sort of see one example on the bottom right. That's one of my favorite fractals. It's Sierpinski's triangle. And you can kind of see that self-similar nature, right? You have the exact same pattern being repeated over and over and over within our fractal. Okay, so like I've said many different times, fractals can be found lots of places in nature, which is useful to us because they are really interesting to explore. And once you understand the basic idea of how to visualize a fractal, I'm going to demonstrate 2 in today's lecture. Once you understand the general idea behind how to visualize a fractal, you can visualize pretty much any fractal that is interesting to you. So we're going to be talking about, I think, 3 or 4 different fractals today. We're going to be visualizing like 3, but the world of fractals is immense. And hopefully once you leave today's lecture, you will know how to visualize any fractal of your choosing. The other important thing, the really interesting thing about fractals is that, as we'll see soon, they can be generated deterministically or stochastically. So we have the tools to build fractals exactly as we want them, but we can also use chaos and randomness to generate fractals. And that should be really, really interesting to you, right? Like, why is it that we can use a random process to generate something that is infinitely self-similar? That should seem just a little bit paradoxical. And that leads us to our last sort of question. And this is one that I like the can math be invented or discovered, or is math invented or discovered question. We won't provide an exact answer to, but I do think is interesting to keep in mind as we go throughout today's lecture. As we know, our world is very chaotic, right? A lot of you have probably heard of the butterfly effect. You maybe know a little bit about dynamical systems. We live in a world where very small perturbations can lead to very big outcomes. And we know that chaos is an important part of our world, and yet we still see infinite self-similarity show up a lot in nature. We see it a lot in the biological world. And I think that raises maybe some interesting mathematical questions, but also some pretty interesting philosophical questions if you're interested in engaging with this sort of thing. The other thing that I think is cool about this sort of interplay between chaos and fractals is you don't need to be a hardcore mathematician or a physicist or a biologist to engage with these topics. I think that even just during today's lecture, you'll probably have a couple of ideas about what you think the relationship between chaos and fractals or self-similarity is. Okay, so moving right along, where can you find fractals? You can find them in lots and lots of different places. A couple of my favorites, as I mentioned 2 lectures ago in lecture 1, is snowflakes, right? We see them here in Boston. I think there's still a little bit of snow if you look really hard someplace. You can also find them in your food. The second picture I have up here is Romanesco broccoli. And I absolutely love Romanesco broccoli. I don't think I've ever eaten it, but I have seen lots and lots of pictures of it. And I think it's really, really cool how precisely self-similar Romanesco broccoli is. Like we said, lots of patterns in nature aren't going to be super duper self-similar. Romanesco broccoli is one that is, or it tends to be quite self-similar. Another one that we see every single day is trees. Branches are going to be self-similar in lots of interesting ways. And we're actually going to be visualizing both snowflakes and trees during lecture today. Those are going to be the 2 main fractals that we focus on. And even though fractals have lots and lots of variety, what I sort of want to show off with this last set of pictures at the bottom there is that there's a lot of fractals that are quite similar to one another, and they occur in all sorts of different places. We see a couple of blood vessels, like human blood vessels in the bottom left, and then we see the veins of plants in the bottom middle, and then a river in the bottom right. And I mean, it really doesn't take a lot of squinting to see the similarity between all of these things. And like I said, lots of interesting philosophical questions if you're interested in engaging with that sort of thing. Okay. I also want to very briefly talk about fractals and paradoxes. And this is, I think, the very last slide before we get to do some actual coding. What I think is interesting is that fractals behave in ways that may seem paradoxical. And 2 really good examples of this are the fractal coastline paradox that you can see on the left and the Van Koch snowflake, which you can see on the right. And we'll talk about how each of these are paradoxical. So with the coastline paradox, very common fractal again is the coastline of a lot of different countries. If you look at a coastline, it'll be a little jagged. And if you zoom in, it'll be still jagged. If you keep zooming in, it will keep being jagged, and you'll see different pieces that you couldn't see when you were zoomed out. And what's interesting is if you take the perimeter of a coastline, the length of that coastline is going to differ based on the increment of like the ruler that you're using. And this shouldn't be too surprising to you, especially given the visual here. But if you use maybe like a 100-meter stick to measure a coastline, you're not going to be able to get those exact intricacies that you could if you were using like maybe an inch-long stick or something like that. And the smaller that we get with our measurement, the larger the overall perimeter is going to be. And that should be somewhat interesting because of its paradoxical nature. The other interesting paradox that I want to cover, and again, there's lots and lots of them when it comes to fractals, but the other one that I want to cover is the Van Gogh snowflake. Again, moving sort of quickly through these because I really do want to get to the visualization. But the Van Gogh snowflake it's super easy to create. And actually, let me go ahead and stop sharing my screen for a second so that we can maybe take a look at how to create it on the whiteboard here. So there we go. All right. So the Van Gogh snowflake, super simple. In the animation that we showed on screen, we did this with an equilateral triangle. Instead, just for the sake of drawing it out, we're going to do it with a simple line here. So the way that we first start out is we're going to take a line, we're going to divide it up into thirds, and then the middle third we're going to turn into a triangle. And so this is step number 1. Step number 2, we start with this and we do the exact same process. So we start with something that looks a little bit like this. And then for every single straight line that you see, we're going to repeat that process. So here's a straight line, here's a straight line, here's a straight line, here's a straight line. For each of those straight lines, we're going to divide that up into 3 equal parts. And then the middle of every single one of these parts becomes a sort of like triangle slope looking thing. And we repeat that process. And so as you'll see, in step 3, it looks a little something like this. And I'm already drawing lots and lots of triangles here, so you might want to, so you might already see why we don't want to do this sort of thing by hand and why generative art is likely a very good tool to use for doing things of this nature. But it turns out if you repeat this process over and over on, instead of just an ordinary line like this, if instead you do it on an equilateral triangle like this, you come up with this very pretty snowflake. And the paradox here, right, is that every iteration, the perimeter of our snowflake is increasing. It's increasing by a factor of 4/3, but the area is staying the exact same. And so what we eventually get with the Van Gogh snowflake, the interesting paradoxical element, is we've created something that has an infinite perimeter, but a finite area. So if you wanted to, paint this thing, you could do that with a finite amount of paint, but if you wanted to draw around the outside of it, it would take you an infinite amount of paint. It doesn't make any sense. So lots and lots of very interesting paradoxical elements that pop up when we talk about fractals. Again, just very introductory survey stuff before we get into how to create, excuse me, these fractals. And that's what we are going to spend the rest of our lecture time doing. The 2 big ideas. Yes, question? Yes, it's the Van Gogh snowflake. That's spelled V-A-N-K-O-C-H. If you just look that up, you should be good to go. Eventually, as we continue iterations of the Van Gogh snowflake, the perimeter will become infinite, but the area will remain finite. Yes, it will converge. The area will converge, but the perimeter will not. It should be paradoxical because it shouldn't make sense that you have a finite area but an infinite perimeter. I mean, I think the best example of that is probably what I mentioned with the paint. It shouldn't be possible for you to be able to paint the inside of an entire figure using a finite amount of paint, but then be unable to paint around the outside of it, even with an infinite amount of paint. And I think if you're interested, we can probably discuss this a little bit after lecture, but I think the reason for this is it has to do with the fractal dimension of the Van Gogh snowflake, and I think that we won't cover fractal dimensions, but it's, I think, a very integral and basic part of fractal math that should be at the heart of this paradox. The coastline paradox? Yeah. Okay. All right. So here's how we're going to divide up the rest of our time in lecture. The first thing that I want to show you is a stochastic method of creating fractals. And so we're going to be playing something called the chaos game. It's a really simple game. It's really, really easy to code out, but it creates some really, really pretty fractals. And so that stochastic sort of formula is how you can generate a very limited amount of fractals. If you want to generate a lot more fractals, you need to do that maybe more deterministically using recursion, which is what we'll cover in the latter half of lecture. And that's going to be a much more powerful tool, but it's also going to be a little bit more complicated. So if this is your first time coding, that might be a little bit harder to follow, but it will be more powerful. Okay, so let's start with the chaos game. This is a really interesting one. So the way the chaos game works is we want to take some sort of n-gon, some sort of polygon with n sides, and we want to randomly, well, not entirely randomly, somewhat formulaically, distribute points within this n-gon. And so the easiest way to think about it is using just a triangle. Can everybody on Zoom see that okay? Yeah, that should be fine. Okay, so the easiest way to get started is just to visualize a triangle. And what we really want to focus on are the vertices of this triangle. And everything that I say for triangles here is going to generalize for any polygon of n sides. So we really want to focus on these vertices. I'll go ahead and label them A, B, and C. And the way the chaos game works, and again, this generalizes, is we want to randomly pick a point somewhere inside of our shape. Maybe we pick a point here. Then we want to randomly pick one of the polygon's vertices. Maybe we start with B. And we want to plot the distance between our point and point B. Take the midpoint of that distance, maybe that's somewhere around here, plot that, and then we want to repeat this entire process. So we started here, now we're here. We want to randomly pick another vertex. Maybe we pick A. We want to calculate the midpoint, maybe that's somewhere around here, and repeat this process. Does anybody have an idea of what we'll get if we keep plotting these points? It might not be clear to you, but there are some constraints that stop points from being everywhere within our triangle. So will we have any points within here? If I wanted a point to exist within here, would that be possible? Well, where would our point have to start in order for it to be plotted here? In order for this to be the midpoint between C and something else, that might need to be outside of our triangle, right? Which is not how we start this game. We always start within it. And it should be clear to you, or it should be pretty easy to convince yourself that once we start inside of our triangle, we never leave it. And because this is a triangle, we certainly can't have a point here because that would mean that we started here, which is outside of our triangle. And so it should be somewhat clear to you that there are some constraints on where points can lie. It might not be entirely clear to you, and it's actually quite difficult to visualize what the structure will look like after we keep plotting these points, but there are some sort of restraints that we're putting on ourselves. And so maybe we'll also talk very briefly about why these restraints exist and why they create fractals after we work on plotting these points. Does anybody have any questions so far about what we've talked about? We moved pretty quickly through the beginning, but yes. I'm saying that no point will exist within this small triangle as long as we start, within the original. This will eventually create a fractal. So this process will create a fractal. And again, it might not be immediately clear why. It may just be clear that there are some constraints on where points can be and can't be, but it might not be clear why this creates a fractal. Okay, so we'll have that conversation in just a second. What I want to do now is actually go through the process of coding this out, because I think it creates some very pretty visuals, and it might explain, or it might help you understand why the chaos game actually does create fractals. So in order to do that, we'll go back to screen sharing, and we'll head over to our standard processing sketch. So by now, you guys should be very familiar with how we want to set up these drawings. Void setup to set up our sketch. That's going to run once at the very top, and then void draw for our infinitely repeating draw loop. Again, we'll do our usual. We'll just go ahead and make this sketch full screen. And now we got to think about how we want to recreate this process. How do we want to create the chaos game? Well, all we really need, right, is the vertices of our triangle. Once we have that, then we can go ahead and begin plotting points. Any ideas on how we know where the vertices of this triangle are going to be? How we can calculate where the vertices of any n-gon polygon should be? This is a tough one, but we have already written out the code for this. We've already discussed the formula for this.
Isn't that you input the vertices?
Yes, so we do, so we can manually input the vertices, definitely. But we also might want a very scalable and generalizable way of knowing where the vertices of any polygon with n sides are. Because remember, the chaos game is generalizable to any polygon. And so if we want this visualization to scale up, we might not want to manually figure out where the vertices are every single time.
Would they be a certain distance around the circle?
They absolutely would. I saw that in chat as well just a second ago. Yeah, so we talked about how we can figure out where points lie along a circle. If we do that for n points, where n is the number of sides that we want on our polygon, we should also have the vertices to our polygon. And so to sort of prove this to you guys, let's go back to our board super quick. Yes, exactly. Yeah. This is the polygon. We can think of it as circumscribed, I think is the right term.
So it has to be a regular shape.
It does, yeah.
But that's not generalizable then.
Why not?
You're only talking about polygons that all the vertices lies on a circle.
Yes. Okay. Yeah. Yes, you are right. We don't want to play the chaos game with. Actually, this might be really interesting to do. I've never considered polygons that aren't just with equidistant points around a circle. It might be really interesting to play the chaos game within that. But you're right. For the sake of this, we will only be talking about regular polygons that can be circumscribed within a circle. Okay, cool. Sorry, you guys have just been looking at the Blackboard for a couple minutes. But right, so when we talked last with our coffee cup visualization, what we talked about was creating endpoints around a circle. And in order to do that, we just used the super simple formula r times cosine with our angle for the x-coordinate, and our y-coordinate being r times sine of our angle, where r is the radius, and of course angle is just, whatever angle that we want between, if we're talking in radians, this has to be between 0 and 2 pi. And so if we want just the vertices of, say, like a triangle, then yes, question.
Can you maybe make the font writing larger?
Can I write larger? Yes, I absolutely can. And then you guys also might have a little bit of a shadow. Is that good to people on Zoom?
Yeah, that looks fine though.
Okay, cool, perfect. Can you see this in the back?
If I try hard every second.
Okay, here, let me go ahead and rewrite it just a little bit bigger for you then. The x-coordinate is going to be r times cosine of our angle. Hopefully that's better.
Yeah.
And our y-coordinate is going to be r times sine of our angle. And that angle has to lie within 0 and 2 pi. And so if we want the coordinates of our triangle, all we need to do really is just take a circle and we just find 3 equidistant points along that circle, and that gives us the vertices of our triangle, right? That gives us the vertices of our triangle. So as long as we know those, we're good. And we can repeat this process, this exact same process, for a square, a pentagon, so on and so forth. We may need to mess with the angle just a little bit, but like the overall concept should be sound. And so we know exactly how to do this process. We've done this before. So let's go back to our code and at first just create a triangle, and then we can actually start to play the chaos game within that triangle. All right, okay. So if we go back here, the first thing that we probably want to define is the number of points that we want around our polygon. We can just call this num points, and maybe we start this off at something like 0. And the other thing that we also want to keep track of is the radius, right? That's going to be a part of the equation that we just mentioned. So we can just call that r, and we'll start this off pretty big. Maybe we'll start it off at like 100. And so if we want a polygon with 3 sides, then I think all that we need to do, and again, this is really pulling from the code that we wrote last lecture, we want to generate a point for between 0 and the number of points. So for every single point, we need to figure out its location and plot it. And so we can go ahead and do that just by drawing a circle in that location. Remember, x is going to be r times cosine and then the angle. And we know that the angle goes between 0 and 2 pi, so we want to have num points equidistant, like linearly interpolated, between 0 and 2 pi. And so the way that we can do that is just I divided by num points, and that's just going to give us a fraction that goes between 0 and 1 times 2 pi. That's going to be our x value. The y value should be the exact same, except with sine. And we will give this circle maybe just a diameter of 10. Let's go ahead and plot that, see if we get what we're looking for. Okay, we see a little bit of a circle here. And again, this is my mistake. This is because we're drawing around the origin. And remember, the origin is always going to be top left. We want to move that origin. We want to move our 0, 0 point down to the center of our canvas. And remember, the way that we do that is using that translate function. So we can go ahead and translate our canvas to be in the center of the screen. So let's go ahead and rerun that. And yeah, we see that we have a triangle here. Like I mentioned, the exact like angle that the triangle is at may not be what we're used to, but this does indeed create a triangle. So like I said, this should be generalizable. And so in order to sort of prove that to you guys, let me go ahead and change this from just 3 to be maybe 4 or 5 or something like that. So 4 should give us a square, and indeed it does. 5 should give us a pentagon, so on and so forth. So actually, in the spirit of this being generative art and everything being scalable and animatable, how about we increase num points by 1 every single iteration? And so if we do that, what you should see is a bunch of like polygon vertices showing up on screen over and over. So we're clearing the screen, we're drawing where all of the points for a polygon with num points should be, and then we're incrementing the number of points and we're repeating the entire process. So this is going to go super, super fast when I run it the first time, but then I'll slow it down for you guys. But as you can see, we are indeed increasing the number of points. Let's really slow this thing down just to prove to you guys that this process is working. So we have 3, then we have a square, pentagon, hexagon, septagon, octagon, nonagon, decagon, so on and so forth. So we'll go ahead and, I accidentally stopped sharing entirely. Just wanted to stop that sketch. Okay, so now that we actually have our points, let's go ahead and start playing the chaos game. So how do we want to do this? How do we want to approach this? Well, we know that we always want to keep track of a point within our game, right? And so we'll probably need a vector object for that. Just like we did last time, we can go ahead and use a p-vector for our position. And maybe we can start that p-vector. Remember, we always want to start our point inside of the polygon that we're using. If we start it outside, then we're going to get a lot of weird, undefined behavior. And we won't get those constraints that we talked about just a couple of minutes ago. So if we know that we are drawing always around our origin, then certainly our origin should be a good place to start. 0, 0 should always be inside of the shape that we've created. And so maybe we can start our point there. So we say our position is a new p-vector with, we want to start it at the origin, so we want to start it at 0, 0. And remember that 0, 0 coordinate is going to get shifted to be the center of our canvas by this translate function here. Okay, so we have a position. We know how to calculate the vertex for any given point. Now what we need to do is randomly generate a vertex, find the midpoint between our current position and that vertex, and then plot it. Right, so let's break that down. Maybe let me get rid of this. Let me get rid of all of this, actually. So as long as you guys understood how that code works, it'll be really, really easy to rewrite. So step 1 is just going to be randomly figure out the next vertex. Step 2 is going to be find the midpoint between our current point and the next vertex. And then 3, all we're going to want to do is plot it. Okay, so now that we've broken this down, let's go ahead and implement each of these. If we want to randomly figure out the next vertex, and we know that there are num points, number of vertices, then all we really need to do is just generate a random number between 0 and num points, right? And that'll point to a specific vertex. So maybe we'll say int next vertex is equal to, we want to randomly generate a point between 0 and num points. And if you guys remember from our first lecture, that returns a floating point value, which is no good if we want an int. So we'll go ahead and cast that to an integer. Okay, so we're done with step 1. Now we need to do step 2. We need to find the midpoint of our current point and the next vertex. In order to do that, we actually need that next vertice's coordinates, right? And so we were able to generate all of the coordinates using our for loop. We don't want to do that here. We want just a specific coordinate. And so the way that we can do that, and feel free to stop me if this gets complicated, but the way that we can do that is if we want to figure out the next vertex coordinates, the x value for that is going to be, again, from our formula, r times the cosine. And before, we were using I as the index to interpolate between 0 and num points. But here we know exactly what I is. I is the next vertex. And so we can use next vertex divided by num points, and that's going to give us a fractional value between 0 and 1 times 2 pi. And that's going to be our x-coordinate. Our y-coordinate is going to be very, very similar. It's going to be the exact same thing, but with sine. And that should be it. That should be the coordinates of our next point. Looks like we have messed something up. Oh, it just says the value is not used. Okay, that should be fine. All right, any questions at this point? Does everybody follow everything that's happening so far?
So radius is the same?
Yes, radius is the same.
Midpoint
Right.
between...
Okay, perfect. Yes. Do we have a question?
I guess I'm just trying to ask for a pause.
Oh, yeah, of course. We can do that. On Zoom, any questions? All right, perfect. We will we'll go ahead and forge on then. So we found the next vertex coordinates. What we actually care about is the midpoint between our current point and the next vertex. And so the way that we want to calculate the actual midpoint is, if you guys remember midpoint formula, it's super duper simple. It is, here, let me go ahead and write it on the board for you guys, just in case anybody would find that helpful. Midpoint formula is super duper simple. It is just x1 plus x2 all over 2, comma, y1 plus y2 all over 2. So in this case, x1 and y1 are going to be our current position, and then x2 and y2 are going to be the coordinates of the next vertex. So that's p vector next vertex chords. And if we find the midpoint, then we will have effectively just repeated the chaos game. We'll just find the next point in the process. So if we want to do that, we can go ahead and say that our new position, right, is going to be a new p vector with the old x position, so the old x position plus the next vertex coordinates x position, all divided by 2, plus the exact same thing, or sorry, not plus, comma, the exact same thing, but with the y's. And so that should be our new position. And so we're done with step 2 here. Finally, step 3 is just going to be to plot this thing. So we can just go ahead and plot a point at positions x and the positions y. And let's go ahead and see if this works, if this gives us what we're looking for. It did not. Oh, you know what? Because I'm drawing black on black here. The stroke defaults to black, and I was setting the background as black, so we wouldn't have seen anything. Okay, actually here we are seeing something. Before it gets too big, I want to go ahead and increase the radius so that it's a little bit clearer what we're seeing. And I also want to make this animation run faster because it's going to take quite a while if I don't. All right, let's go ahead and run this. All right, hopefully you guys can sort of see a pattern emerging. Can everybody here see that okay? I'm not sure how good the projectors are. Yeah, you guys can see that, right? Cool, okay. Yeah, so what you see here is Sierpinski's triangle. That was the very first fractal that we looked at Actually, the very first one we looked at was, I think, the Mandelbrot set, but this was the one that was looping on that second slide. So why is this happening? Why is this working the way that it is? Any ideas? Any thoughts?
So this is basically generating the same triangle in all three vertices, right?
Right,
Like
exactly.
half of it.
Yeah. So the idea behind why the chaos game is working in this instance, right, is if we go back to our whiteboard, the same principle that made it such that it was impossible to get any sort of point within this middle triangle here, the property that you had to be outside of the triangle to get in here, is replicated over and over for every single one of these inner triangles. Because you cannot get anywhere in here, you cannot get anywhere in here, because to get within this smaller triangle here, you would have had to start within this big triangle. And to get within this big triangle, you would have had to start outside of our triangle, which we know isn't possible, right? And in order to get within this triangle here, you would have to start within this triangle, which would require you to start here, which would require you to start out here. And so because of that restriction that we have, which is a function of the fact that this is a triangle, right? If this was a square, it wouldn't work the same way, and we'll talk about that in just a second. Because this is a triangle, and we have to start inside, you can never get here, so you can never get here, 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 so on and so forth. And so that creates the process which eventually generates Sierpinski's triangle. And this process is self-similar because the restrictions are self-similar. Any questions about that idea? Awesome. Okay, so let's keep going with this process.
Triangle vertices.
Yes, exactly. Every time we are moving towards a one of the vertices of the polygon.
Of the initial polygon.
Yes, of the initial polygon. Okay, so right, our favorite thing to do, right, is to ask what if questions with every single one of these visualizations. And so the next thing that we'll look at, which will generate some really, really interesting stuff, is what if we were no longer using just a triangle? What if we were using something else? And we'll take a look at, maybe we'll take a look at a square. Does anybody have any predictions on what might happen if we use a square instead of a triangle? No. Do we have the same restriction with a square that led to gaps in the triangle? I don't think so, right? You can get anywhere within the square from any other point. And I think that should be the case. We can sort of intuit that. Maybe while we think about that, we'll go ahead and run this animation and we'll see if that's actually the case. So I claim that this circle should be, or sorry, this square should be entirely filled in with points because it should be possible for us to get anywhere within the square from any, from like some given starting point that's also within the square. And I think we're slowly getting there. So yeah, this process didn't work for a square, which is interesting. Any thoughts on what would happen if we used a pentagon? Let's go ahead and try it. So we'll go ahead and stop this one just because I think it's clear that our square is fully filled in. Let's go ahead and try what happens with the pentagon. And we'll go ahead and I'll go ahead and tell you, you should see something somewhat interesting with the pentagon. And I think you might already start seeing just a little bit of that. Hopefully my folks online can see the points okay. I know they're super duper tiny on my screen, so if needed, I can increase the size of those points. But we do see a little bit of structure forming here too. We definitely have gaps, right? You should see the center definitely has a gap. The outside definitely has a couple of gaps. And that should be clear to us exactly why. See, in order to get in the center, we would have to start, again, outside of our pentagon. And in order to get here, we would have to start in the center of our pentagon. And in order to get here, we would have to start here, which we know isn't possible. That exact same property that led to restrictions on the triangle is leading to restrictions on the pentagon. And so this should be somewhat interesting to you for another reason, which is that generally when we think of fractal creation, we're thinking of it as an additive process. We are doing something new every single step. We're adding to the process. That's what we saw with the Van Gogh snowflake. This process is somewhat reductive. We're putting restrictions on where each of these points can be. And I think that's another interesting element of creating these sort of fractals stochastically. All right, interesting stuff. All right, so the next thing that I want to do is introduce you guys to one last what if while we talk about stochastic fractal creation, and that's going to lead us to our snowflakes. And then after our snowflakes, we'll go ahead and switch gears to recursion and talk about how we create trees using recursion and processing. Okay, so let's go ahead and stop this process. A cool what if, right, is not just what if we changed the amount of sides that the polygon that we use has, but what if we put restrictions on where or which vertex we're allowed to go to. And so that leads us to something called the restricted chaos game. And so you'll remember we didn't see any sort of fractal when we used our square, right? We just had a completely filled in square. And so what might be interesting is the condition that we can't choose the same vertex twice in a row. So if we start with our triangle here, go ahead and stop sharing again. If we go ahead and move over here to our triangle, what if we were to generate a point, say we choose vertex B right here. So we find the midpoint, which is right here. And then it's very possible, right, using the chaos game in its simplest form, that we once again choose B and we get even closer to B. So on and so forth. This wasn't a problem in the creation of our fractal when this was a triangle, because there were restrictions put in place by the shape itself. But placing this restriction on a square, which doesn't have the natural restriction of like not being able to fill in that center triangle because of the way that the shape is formed, adding this new restriction should create maybe something of some interest. So we'll go ahead and add this restriction and now play the restricted chaos game. And this should be a very, very simple modification to our code. A lot of you will probably do this modification a lot faster than I will if you're following along. It is close. We're not fixing the next vertex. We're fixing what the next vertex cannot be. So if we chose vertex B initially, then the next step, we're not allowed to choose vertex B again. We can choose vertices A or C, but not B. Great. Similarly, if we start with vertex A, you can't use A on the next round, but you can use it on the round after that. Okay, so if we want to keep track of this, the sort of like easy, naive way to do it is we need to create a variable to store what the previously used vertex was, right? And we want to make sure that our next vertex is not the same as our previously used vertex. And so this should be simple. We can just create an integer that stores the previous vertex. And maybe we can start that out at -1, just because we know for sure that we can start anywhere with that first iteration, and -1 is not a valid vertex, so we should be fine there. And now we can say, maybe step 1.5 is make sure that the next vertex is not equal to the previous vertex. So maybe we can say, while our next vertex is equal to our previous vertex, let's go ahead and randomly generate a new point. So we'll repeat this process while next vertex is equal to previous vertex. And then once we are down here, we've ensured that next vertex and previous vertex are not the same. And now we want to say that our previous vertex then becomes our next vertex. Does that make sense to everyone? Awesome. Okay, so let's see what happens here. I'm gonna go ahead and instead of using a point here, I'm gonna go ahead and use a circle with radius, or I guess diameter. Keep messing that up. Circle with a diameter 5. And I'll go ahead and also in our setup method use something called no stroke. So no stroke, all that does is initially, whenever you draw a circle or any sort of like basic shape in processing, it has a stroke which defines the outline of the shape, and then a fill color which defines the inside. I just don't want an outline on any of these, is the only reason that I'm doing that. Oh, and our fill color should be, maybe we'll do fill color white on a black background. So background is black, our fill color is white. Let's go ahead and run this thing with a square. All right, so that should be somewhat interesting to you guys. So we've created this sort of like interesting little like lattice, maybe snowflake-esque form. And so just in the interest of time, we won't talk about exactly why this snowflake is forming the way it is. But it is forming, and it turns out we can repeat this process with all sorts of other polygons. So this is our very first snowflake. Let's go ahead and change num points to 5, and let's repeat this process with a pentagon. Now, I already know this one's going to look very pretty, so I'm willing to wait a little bit more to get a nice, pretty picture out of it. So let's go ahead and run that, and we get an even more intricate snowflake. Right, and these snowflakes look surprisingly close to like snowflakes in nature, right? Like if you went out and you like looked at a snowflake and you put it under a microscope, it would not look too far from this, depending on like the type of snowflake. And I think that's really, really cool that we were able to generate this completely randomly by adding just a couple of very basic restrictions. And I think that process really makes you think. Okay, just for fun, let's go ahead and see what would happen if we used a hexagon instead of a pentagon. And you can repeat this process at home as long as you have a big enough monitor, enough patience, and you set the radius size to be small enough. You can do this with like a octagon or a nonagon or even a decagon. The pattern might not be as clear, but you will definitely get a pattern of some kind. Yes?
Just want to make a, it's not a comment, but share, just want to share for those who have used Windows XP.
Mm-hmm.
Have you used Windows XP?
I have not. Windows XP is before my time.
So so basically I grew up using Windows XP, and then the screen, there's a screen protection, which means
yeah, the screensaver, right?
Screensaver does something like that.
Interesting. Okay, I never knew that.
So randomly generate patterns, and then it ends up with a beautiful pattern. And
incredible.
Today I learned.
Awesome. Very nice. Okay, I'll have to check that out. I did not know that Windows XP had a screensaver like that. So I guess I'm dating myself a little bit, which is totally fine because I'm 21. Last thing that we'll do before we move to deterministic fractal creation is, you guys know me, I love adding color to like generative pieces like this. I think it's a lot of fun because snowflakes are not very interesting colors in the real world. So let's go ahead and add a little bit of color. And I want to, my vision for this is sort of like a gradient, which starts at the very center and then it changes color as we move outside of the center. And so I'm going to show you guys very, very quickly how to do that. We're already low on time, which sucks. I had no clue how the hour goes by. But we will add some color. I won't show you guys the intricacies of this, but I will post the code. So if you're interested in how we do this, it's a very versatile method and you can follow along at home. But the idea is that we want to set our fill color, right? Because this is a circle. We want to set our fill color to be a function of the distance that a given circle is from our center. And so we can say that, remember, if we don't use any color mode, processing defaults to using RGB, but as we talked about last class, we can use HSB as the color mode to instead use our parameters as hue, saturation, and brightness instead of red, green, and blue. So we want to set our fill color. Maybe we always want to be very saturated and very bright, and so we'll set 255 for saturation and brightness. But for our hue, maybe we want to map that. Maybe we want to map that as the current positions. We want to map the, how do we want to do this? We want to map the distance that our circle is from the center to be some value between 0 and 255, because that's what our hue parameter takes in. So we can map the distance, and remember this distance formula function takes in x1, y1, and then x2, y2. We want to find the distance of our current position to our center, which is going to be 0, 0. So we want to map the distance from 0, the distance is going to be 0 if this point is right at the center, to some like pretty big value. We could use Pythagorean theorem to calculate this really quickly, but I'm not going to. I'm just going to give it the value height. So we're going to map our positions, or the distance of our circle from the origin, from 0 to height, to a value between 0 and 255. And really this should be down here because we set our position down here. So let's go ahead and run this thing. Okay, cool. And we see that we have a new pretty snowflake forming and we get exactly what we were looking for. We get this nice little gradient of colors coming out from the center. So lots and lots of fun to play with colors. It's also super easy once you get the basics down of how the color channels work. And I think it leads to some pretty cool stuff. All right, any questions about anything that we've covered during this segment of the lecture? All right, we have 30 minutes left, so we're just going to breeze straight through to the very end, which is deterministic fractal creation. So, like I said, we're going to be doing a little bit of recursion here, and if you're not familiar with recursion, it is complicated. So you'll have to bear with me a little bit, maybe do a little bit of Googling. If you are familiar with recursion, this process should be super simple to you guys. You might have to listen to me saying stuff that you already know. So we created snowflakes. Now we want to create trees. The tree creation process is this that we want to focus on is going to be super duper simple. And you guys might have seen visualizations like this before. But today you're going to learn exactly how to make them. So what we want to do here with our tree is we want to create a tree where we start with a branch, and then we want to, at some angle, create two smaller branches that come out of the initial tree, and then from those, two smaller ones again, so on and so forth until we get our final tree. And it should be pretty clear to you guys why this process is self-similar, right? every single branch. If you look at this branch by itself, if you pretend there's nothing other than this branch, and you rotate it, it's the exact same as this branch, right? And so this self-similarity creates a fractal, and this fractal actually ends up being really, really pretty once we add enough of these. So scale is going to be important here. Oh, one thing that I meant to mention at the very beginning of lecture, which I didn't. Processing is a very imperfect tool for fractal creation. You certainly can, and people have created absolutely beautiful fractals in processing. But if you think this is going to be the focus of what you're interested in, I think maybe start with processing, but there's tons of better tools to create very intricate, very pretty fractals. And so if this is your focus, your bread and butter, processing might not be the right tool for you. All right, awesome. Let's go ahead and get started with figuring out exactly how we want this process to work using recursion. So is anybody not familiar with recursion? Does anybody want me to like define recursion, what that might look like? Okay, perfect. So what we want to do, and we're going to be messing a lot with coordinate systems here, is we want to create a branch, and we can make this an object. And actually, I'm gonna go against what I said at the very beginning of this course, which is try and think about things as object-oriented as possible. We're not going to think about this in a very object-oriented way, but that's only for the sake of time. It's going to take us a little bit longer to set this up as an object. But when you do this at home, consider how what we do in lecture here today would translate to an object-oriented structure. But really what we want at its core is just going to be some sort of branch, and each branch has two children which extend out at an angle, right? And so the way that we can think about this is in terms of origins. If we start our origin down here, then all we want to do is draw a line upwards, right? And that's it. So we're going to think about this as one. Hopefully you guys can see that. Let me move this just a little bit so that it's clear. Okay. Yeah, let me know on Zoom if that's not visible, but I think that looks okay on my screen. So step 1, move the origin. Step 2, draw a branch. And that's it. Those 2 steps are really all we need. And so we start by moving the origin down to our base, and then we draw a branch going up. Now we want to move our origin again, and instead of moving it, like translating it, we want to translate our entire coordinate plane so that it looks this way. It looks up at this angle. And then if we draw a line that is straight, but our coordinate plane is angled, then we're going to get this line right here, right? And then we want to take our coordinate plane, put it back to where it was initially, and then move our origin and our coordinate plane again so that it tilts this way, draw a branch, and then repeat that entire process, right? If we're here, then we just drew our branch. Now we want to move our origin. We want to tilt it back this way, draw a branch, go back to our initial point, move our origin in our coordinate system, draw a branch, so on and so forth. Does this idea make sense? Does the coordinate plane moving is like really confusing at first? At least it was for me. It doesn't come naturally, but hopefully when you guys see this sort of drawn out this way, it makes a little bit more sense. And so maybe start thinking about the what ifs with this visualization. What if something changed? What can we change very easily? How can we make it change? Things like color are always something that we can mess with, but in this instance, there might be something else that we can mess with. All right, cool. Let's go ahead and start coding. Looks like we have a couple of minutes. This is very, very short code. It should be like maybe 15 lines of code. So as long as the concept is somewhat clear, I think we should be good. So we'll go ahead and save this. This will be called snowflakes. Let's go ahead and create a new processing window. Our usual void setup. Go ahead and full screen. And then let's go ahead and void draw. Okay, so what do we need? Well, we need to keep track of the radius or the angle that we're moving at, right? This tree would look very different if we like moved at like a very small angle and every single angle was very sharp. And it would look very different if we had like a very flat angle, if we had like a 90-degree angle that branches came out of. And so we want to keep track of that. And so maybe we can say the float angle that we have, is going to be something like, I don't know, pi by 4. All right. And so now what we want to do is let's go ahead and create this branch function. And this function is what we're actually going to be using to do like the heavy lifting here. This is going to be the function where we take our coordinate plane, draw the branch, move the coordinate plane, draw the branch, like the meat of the visualization. And so as you guys know with recursion, we're going to need some sort of recursive step and some sort of base case. And we'll talk about exactly what that is in just a second. The first thing that we want to do, though, is we want to go ahead and draw our branch. And really all drawing a branch means is just drawing the length of it, right? And so we just want to draw a line. Maybe, remember we've been talking about this in terms of the origin. We always move where our origin point is. So we'll start from our origin, and we just want to draw a straight line up, right? And this straight line up will mean an angled branch because we change our coordinate system. And so all we want to do to draw a straight line is go from 0, 0 to some length up. And maybe we don't know exactly what that length is. Maybe we just outsource it to a variable. And so this should draw a straight line. The only problem is this is going to draw a straight line down. Remember, processing minutia, down is higher coordinates and up is like smaller coordinates. So instead of drawing down, we want our tree to draw like pointing upwards, and so we'll use negative length here. Okay, so our length does not exist.
To share the processing.
Oh, I'm so sorry. Have I not been sharing that so far?
Yeah, no worries.
Oh, my bad, guys. Okay, there we are. Okay, so you haven't missed much. Everything there so far should be the exact same. The one variable that we're using here that we haven't actually defined yet is the length. Now, what might be interesting is to draw each branch's length differently based on where it is in our tree, right? It makes sense that in our tree, the base branch should be a lot longer than the branches that move outwards from it, right? And that's sort of like a real tree structure anyway. A twig is going to be a lot shorter than the trunk of the tree itself. And so let's go ahead and mimic that idea. And so maybe we take in a float length. And so all we're doing here is drawing this line. And now we need to do the hard part, which is moving our coordinate plane and then redrawing lines, right? And so if we want to redraw our coordinate plane, we want to, here, let me stop sharing and we'll go back. Okay, so all we've done so far is create this line right here. This line. And our coordinate plane, our origin point starts here. In order to create the next part of our tree, we need to move our origin from where it is currently up to where our branch has just ended. And then we're going to want to rotate our entire coordinate system based on that angle that we defined earlier, so that the next time that we draw a branch, it will go in the direction that we want, either of these directions. Everybody good with that idea? Perfect. Okay, back to processing. So what we want to do is we want to take our origin point and we want to translate it up. We want to translate it up by the length. And so the new origin will be at the tip of the branch that we just drew. And now we want to rotate our coordinate plane based on our angle. And so there's this really cool function in processing called push matrix and pop matrix. And the idea behind how these functions work is if we push a matrix, think of it as pushing a new coordinate system onto our canvas. And then we can mess with that coordinate system however we want. And then we can use the function pop matrix to remove that coordinate system that we've just added and made transformations to. So this is a way of messing with the coordinate system of the canvas in sort of like a layer without messing with the original thing. And so we'll go ahead and rotate our canvas by the angle that we defined. And then after we've done that, we want to create a new branch and then rotate that, so on and so forth, right? And that's our recursive step. So after we've done this, we want to create a new branch and do everything that we've done just now on that, except we probably want it to have a smaller length, right? And so maybe we can decrease the length by 1/3 just by multiplying it by 2/3. And so this will create a new branch recursively. We can go ahead and we're done with that branch, right? And so we can go ahead and pop our matrix. And then we want to do the exact same thing on the opposite angle side. Remember, we split off into 2 branches. And so we want to rotate this not by angle anymore, but by negative angle. And that'll create our new branch off to the other side. Does that idea seem okay to everyone? Okay. As we know, with recursive functions, we also need some sort of base case. Otherwise, this would infinite loop. And so maybe we can say, just as a super simple base case, if the length of our branch is too small, if it's so small that we can't even see it anymore, then let's not worry about it. If the length of our branch is less than 2 pixels long, it's not going to be super visible, so we'll just return. We won't want to continue this function anymore. All right, in our draw loop, I think all we need to do is just create a branch with some sort of length. Maybe we'll say length 200. And I think we're off to the races. Let's go ahead and run this, see what we get. Okay, we did not get anything. The reason for that is because we originally want to start our branch at the bottom middle of the screen. And our origin starts, again, top left. And so we need to translate our origin all the way to the bottom middle of the screen, which is going to be our width divided by 2 and our height. And so that should translate it to where we want it to be. Okay, cool. And we got something. This looks somewhat interesting. This looks right? Let's go ahead and check to make sure. Yeah, so we start off with our branch at the very bottom that splits, and then each of those branches split, and each of those branches split, so on and so forth. Pretty cool, right? And this kind of looks a little like a tree. Let's have some fun with this tree for the last couple of minutes that I have you guys. So Daniel Schiffman came up with the code for what I'm about to do. He's also a huge person in processing. Lots and lots of great tutorials on YouTube. Way better than anything I could ever do. Big fan of Daniel Schiffman and his work. So I want to show you guys his idea for making this tree fun and interactive. So what you'll notice is that if I change the angle here, it leads to a completely different tree, right? This tree looks very different. This sort of looks like something you would find in like a desert or like on a safari trek. And so messing with that angle changes the tree a lot. And so why not make the angle interactive? And so the way that we'll do that is we'll say, now let's have the angle of our tree be a function of where our mouse is. And so again, we can use our map function for that. We want to map our mouse's X position from between, remember our origin is going to be at the middle of the screen. And so we want to map it from between our negative width divided by 2 to width divided by 2. We want to map our mouse from anywhere that it could be on our canvas to a value between 0 and 2 pi. And in doing that, I think if we rerun this, what you'll see, oh man, that's not good. We want to clear the screen every single time before we draw. I keep forgetting that as well. Just set this to white. Okay. I didn't spell background right. There we go. Okay. What you'll see is that as I move my mouse, we're getting all of the different configurations that our tree here could have. Let me go ahead and make our radius just a little bit bigger. But what you see, right, is that there are so many different fractals using the exact same code and just changing that what if just a little bit. And I mean, this kind of looks like tree branches. You'd be crazy if tree branches in the real world look like that, right? I'd want to be outside all the time. I would love to see tree branches that look like this. And of course, we're not going to see that in the real world. But I mean, using just a very, very small trick, we're able to get something that looks incredibly cool. Okay, so maybe let's change our branch to start at like 300. And we'll wrap things up in just a second here. And so, okay, we have something that looks very, very pretty. Let's change some more real quick what ifs, and then we'll wrap up. My favorite thing to change is the stroke width here. So right now, all of our branches have the exact same width. That's of course not the way it is on a tree. Just as branches get shorter as you go up, they also get thinner as you go up. And so let's go ahead and change the stroke width to be thinner or thicker based on where this branch is. So remember, the length is going to determine the branch's like height up. And so if we say that our stroke width is going to be, maybe let's say it's between 3 and like 0.5. So we want to map the value of our branch from the smallest that it can be is 2, right? We want to map it from 2, and the biggest that it can be is 300. So we want to map it from 2 to 300. We want to map that to a value between 0.5 and 3. We want to map the length, not the branch itself. And we need to map an integer, I think, is the issue here. Stroke width. What am I doing wrong here? Maybe I need to convert all of this to an integer. That doesn't seem right, though. Oh, you know what? This might need to be a double. Okay, again with the minutia of processing, and even that might not be right. No. Okay, so we want to map length from 2 to 300 between 0 and that.
It should be stroke weight instead of stroke width.
Thank you very much. I appreciate that. I knew it wasn't, I was like, I've done this before. Stroke weight with a lowercase s. Thank you. There we go. Okay, let's go ahead and map that stroke weight, not width. And so now what we see, and I think this is quite pretty as well, a subtle change, but I think it makes a significant difference. Okay, we, for the sake of time, will not play with color, although I will be posting all of this code, as you guys know, and you are more than welcome to play with color and all sorts of other things when it comes to fractals. So we've only made a couple of fractals, right? But really the idea behind how we made this fractal just a second ago and how we played the chaos game should give you a very good insight into how to create other fractals. It really is not that much different as long as you understand how to code out that recursive step, sort of make that visualization, and then play with the what ifs, play with the parameters. I think you guys can make some really, really pretty stuff. All right, so next lecture is going to be on Monday. I know that's MLK. I wish we didn't have to hold lecture on that day, but we only have 2 weeks for the course. So if you guys can make it, that would be really, really awesome. 4:30 here on Zoom, same stuff. And we're going to be playing with, if I remember correctly, automata and life. And that's going to be a really fun one. We're gonna visualize stuff like bird flocking, fish schooling. We're going to create a visualization for Conway's game and a couple of other cellular automata. So stay tuned for that. I'll go ahead and post the code for this right after lecture, and the assignment will be up either tonight or tomorrow. But yeah, thank you guys for coming. Appreciate you guys being here.
Thank you.
Thank you.
Of course.
Thank you, Sidan.
Yep.